Okay, in this class I want to talk a little about Newton's laws with angles. I'm going to move very quickly through my definitions for sine, cosine and tan. Sine is opposite over adjacent, sine is not opposite over adjacent. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tan is opposite over adjacent. Okay, when we're talking about right triangles. So the opposite can be written as the hypotenuse times sine, and the adjacent can be written times the hypotenuse of cosine. The opposite can also be written as the adjacent times tan. So in a right triangle, if I know one of the angles and I know the hypotenuse, I can work out the opposite. The opposite will be the hypotenuse times sine of that angle, and the adjacent will be the hypotenuse times cosine of that angle. Okay. So suppose I want to look at some situation. Suppose I'm just going to initially talk about a situation where everything's smooth so we can ignore friction. I've got a man pulling a box by a rope. Notice the rope is inclined at an angle here. I'm just going to look at that. What's happening here is there's a tension being created in the rope, and that tension is going to be the force on the box. So there's some kind of tension in here. I'm going to say, I'm going to make up a number for that. I'm going to say, suppose that tension is 100 root 2 newtons. Okay, so 100 root 2 newtons of tension in that rope, whatever that works out to be. What we can do here is we can resolve that tension force into its horizontal and perpendicular components. If I, just make up an angle here, that looks like it's 45 degrees. Let's say it's 45 degrees exactly. I can resolve this 100 root 2 into its horizontal and vertical components. Remember, we just said that the adjacent in a right triangle is always equal to the hypotenuse times cosine. So 100 root 2 times cosine of 45. And the opposite is always equal to the hypotenuse, 100 root 2 times the sine of the angle. But if I know my special triangles, which I'm hoping you do, we should know that the legs of a 45, 45, 90 are always the hypotenuse divided by root 2. So that's going to be 100. That's going to be 100. Okay. What other forces are at work in the box? Well, there's going to be a force downwards, which is called the weight. The weight, remember, is a force is always equal to the mass of the object times little g, the acceleration due to gravity. That's just an extension of F equals ma. Also, there's going to be another upward force, which we call the normal reaction. It's a contact force. And so the three forces at work on the box are the downward force, the weight, which is the force on the box by gravity. The upward force here, the normal reaction, is the force on the box by the ground. And then this tension force up to the right, which is in the force on the box by the rope. Okay, and that rope is being pulled, so there's some kind of force. Notice, because I've said that everything's smooth, that means there's no friction. I'm not worrying about friction. What's going to happen here if everything's smooth? Well, I hope you see kind of that the box is not going to just fly up along towards the man's shoulder. The box will slide along the ground as this man moves to the right, pulling the box. It's going to slide along to the right. One thing that means is that all the up forces must equal to all the down forces. So all the up forces must equal to all the down forces. Because if they weren't equal, well then the box would either accelerate upwards or accelerate downwards. Horizontally, well, there's only one force horizontally happening, so there will be a net force horizontally. It's going to be to the right, so I'm going to call this a right positive system. So there is going to be a net force to the right, which means the box is going to accelerate to the right. So if I go to think about this, well, maybe I'm just going to make up some mass. Suppose I said the mass of the box was equal to 20 newtons, and I'm going to say that little g is equal to, well, let's just go with 9.8 meters per second squared. So if I was to draw the force diagram, I kind of have already, but imagine you're in an exam and you're given the picture. The force diagram is just a picture of the box with all the forces acting on it. There's the upward force here, which we're calling the normal reaction. There's the downward force here, which is the weight, mg. The weight of this will be the mass times little g. Remember, weight is always mg. 20 times 9.8, mass times little g. Well, 10 times 9.8 would be 98. Double that. I think that's going to be 196. So there's 196 newtons pulling down on the box. We also have this normal reaction here acting upwards. I also have the tension force pulling up to the right, and we're saying that's equal to 100 root 2. But what did we do? We also resolved that tension force. I'm just going to put this in a different color here. Resolve that tension force into its horizontal and vertical components. We said that was 45, which means this horizontal component was 100 and this vertical component was also 100. So we kind of resolved this tension force. That's my force diagram. If I look at my force equations from that, force equations, I'm just going to think first of all about the vertical forces. Well, the box will not, and I hope this is kind of just obvious, that the box will not accelerate upwards or downwards. It's going to slide across the floor. So vertically, what's going to happen? Well, vertically the forces up are going to equal to the forces down, assuming this box is moving horizontally across the floor. The forces up must equal to the forces down. What are the forces up? Well, there are two forces upwards. There's the normal reaction, which is the force on the box by the ground. But there's also the vertical component of the tension force. There's also 100 newtons of force being pulled up, and that has to equal to the force down, which is 196 newtons. So one thing I can see here is that the normal reaction must be 96 newtons. Now, that doesn't really affect the horizontal motion in this case, but if there was friction involved, it really would. And we look at an example involving friction in just a moment. Horizontally, we're looking at F net equals ma. The net force is equal to the mass times the acceleration. I'm going to consult my force diagram here to find my net force horizontally. Well, there's only one horizontal force, which is 100 newtons. The mass of the box is 20. So I'm getting the net force here, 100, is equal to the mass of the box, which I think I said was 20, times whatever the acceleration is. And from that, you can work out that the acceleration of the box, in this case, will be 5 meters per second squared. Okay, so we can figure out lots of things that are going to happen in this case. Now note, we just looked at if we were on a smooth surface, but suppose I look at the same problem, but I change. Suppose I say now, instead of a smooth surface, we're on a rough surface with friction. And suppose I define the coefficient of friction to be, I'm just going to make up a number, like 1/10. What is going to happen differently? Well, what's the same is we're still going to have a tension force here. We're still going to have the weight of the box acting downwards. Opposing that, we're still going to have the normal reaction. And then finally, in this case, we are going to have some kind of friction force. I'll just call it F, pulling to the left. So in this case, we've introduced a new force. The weight is the force on the box by gravity. The normal reaction is the force on the box by the ground. The tension is the force on the box by the rope. And the friction is the force on the box by friction. Okay. Again, we can go through the force diagram, although it's almost the same. There's only one new force to take in, but we'll go through the whole thing. The force diagram, I'm going to draw my forces. The weight acting downwards. I'm going to stick with all the same stuff. I'm still going to say this is 45 degrees. I'm still going to say the tension force is 100 root 2. I'm still going to say the mass of the box is 20 kilograms. I think that's what I said. Oh, there we go. There's an error. Mass of a box. I said 20 newtons in the previous example. Mass, of course, that should be kilograms. Apologies. M is equal to 20 kilograms. G I'm going to assume to be 9.8 meters per second squared. Okay, so the downward force is going to be the weight of the box, which is mg, which I think we said is 196. Upwards is going to be the normal reaction. Up to the right is going to be the tension, which I said was 100 root 2. And now, introducing our friction here, we're going to have some kind of friction force. So what do we know about these different things? Well, one thing we know about the friction force is that the maximum friction that I can call upon is always mu times the normal reaction, where mu is the coefficient of friction. Okay, that basically depends on what kind of materials are in contact with each other. So in order to find the maximum friction that can be provided, we have to find the normal reaction, we have to know mu. So we're going to investigate. Just like before, we were able to resolve this into its horizontal and vertical components. We said this was 100 newtons to the right, 100 newtons upwards. If I look at my vertical forces, my forces up are going to equal to my forces down, assuming that this box is just going to slide along the ground. My upward forces are the normal reaction plus 100 newtons. There's my normal reaction. There's my 100 newtons upwards. My downward force is 196. Just like before, we can work out that the normal reaction is 196 newtons. So that's 196. The next thing I want to think about the maximum friction that can be called upon. So I'm going to think about the friction. Friction will grow as the tension in the rope increases, and the maximum value it can attain will be equal to mu times R. I think we said mu was equal to 1/10. The normal reaction we just worked out is 196. So we're going to get 19.6 newtons. That's the most friction that can be called upon, and it'll only be called upon if there's more than 19.6 newtons being pulling to the other direction. Here 100 newtons of force is being pulled to the right, which means all of my friction is going to be called upon, so my friction force will be 19.6. One thing to think about, if this horizontal component was only 10, well, then friction wouldn't need to be 19.6, it would only go up as high as 10. But we can create 19.6 newtons of friction here. So I want to think now about my horizontal forces. Horizontally, again, we're using Newton's second law, F net equals ma. The net force horizontally, well, what have we got? We have this 100 newton pulling to the right and this 19.6 pulling to the left. Assuming a right positive system, that's going to be 100 minus 19.6. 100 minus 19.6. That's going to be my net force. And that's going to be the mass, 20, times the acceleration, whatever that is. 100 minus 19.6, I think that works out as 80.4, is going to equal to 20a. And just dividing on both sides by 20, a is going to equal to, dividing by 2 first will give me 40.2, and then divided by 10 will be 4.02 meters per second squared. So this box is going to accelerate. Notice it's positive, it's accelerating to the right because it's a right positive system at 4.02 meters per second squared. Okay? So dealing with angles make it a little bit more complicated, but not hugely. As long as we can resolve, we can make it pretty much the same as everything we've dealt with so far. Okay. So practice some of those problems. The more you practice, the better you get.